This scene deals with the subject many fathers find so difficult.
Welcome to Podcast V0.1, where we break down the latest research and tools for curious engineers. Ever tried booking a flight during peak season, maybe right before a holiday? You stare at the loading spinner, the seat map takes forever to update, and by the time you click confirm, the price has jumped, or the seat you wanted is gone. It's frustrating, right? That sluggishness, that feeling that the system is lagging behind reality, it's a classic symptom of traditional airline reservation systems straining under pressure. Well, a recent paper proposes a way to potentially slash that delay, maybe by as much as 60%, by fundamentally rethinking where critical computations happen. The core idea? Moving parts of the airline's core logic, the reservation system, physically closer to you using edge computing. Let's dive into the problem first. Traditional airline reservation systems, often called ARS, or their modern evolutions known as passenger service systems, or PSS, have a long history. These systems handle everything from booking flights to managing seat inventory and customer data. They often started as centralized mainframes, giant databases managed by airlines or consortiums like Sabre or Amadeus. While many have evolved, perhaps adopting service-oriented ideas or moving to the cloud, they can retain characteristics of monolithic systems. This means different functions. Flight scheduling, inventory management, pricing, ticketing might be tightly coupled. As the paper points out, this leads to several headaches familiar to many software engineers dealing with large-scale systems. First, latency. When you search for a flight, your request might travel hundreds or thousands of miles to a central data center, get processed, and the response travels all the way back. In a system demanding real-time accuracy, like knowing exactly how many seats are left right now, this round-trip time is a killer. It leads to delays and potentially showing outdated information. Second, scalability. Monolithic systems are notoriously hard to scale efficiently. If the seat inventory check module is getting hammered during a fare sale, you often have to scale the entire application, replicating everything, which is wasteful and expensive. You can't just beef up the specific part that's struggling. This inflexibility means systems can buckle under peak load. Third, flexibility and agility suffer. Deploying a small update often requires rebuilding and redeploying the entire monolith, a risky and slow process. This hinders innovation. And finally, reliability. If one component in a tightly coupled monolith fails, it can bring down the entire system. So how does this paper propose to fix this? The core idea, outlined by Baiman Barua and M. Shamim Kaiser, is a conceptual framework combining two powerful architectural paradigms, edge computing and microservices. Let's break down the edge computing part first. Instead of all processing happening in a distant, centralized cloud, the idea is to push latency-sensitive computations out to edge nodes. These are essentially smaller compute and storage resources located geographically closer to end users, perhaps in regional data centers or network points of presence. Think of it like a content delivery network, or CDN, but for computation instead of just static files. For an airline system, tasks like initial flight searches, real-time seat availability checks, and maybe the first steps of booking could happen on an edge node near you. Your request travels a shorter distance, gets processed faster, and the response comes back quicker, significantly reducing perceived latency. But edge computing alone isn't the whole story. This is where microservices come in. The paper advocates breaking down the monolithic reservation system into smaller, independent services. Imagine separate microservices for data filtering, data aggregation, local analysis, and crucially, a service for synchronizing data back to the central cloud. Each microservice handles a specific business capability and can be developed, deployed, and scaled independently. Now, how do you manage these services across many edge nodes and a central cloud? The framework proposes using Kubernetes. As many listeners know, Kubernetes is the standard for container orchestration. Here, it would manage the deployment, scaling, and health of these reservation microservices. If an edge node sees a surge in traffic, Kubernetes can automatically scale up relevant microservices on that node. This provides elastic scalability and improves resilience. If one microservice instance fails, Kubernetes can handle it without crashing the whole system. The next critical piece is data flow and consistency. If you have hundreds of edge nodes processing booking requests, how do you ensure everyone has an accurate, up-to-date view of seat availability? Selling the same seat twice is unacceptable. The paper acknowledges this as a major challenge, managing distributed data consistency. The proposed solution involves using Apache Kafka, a distributed event streaming platform. Think of it as a central nervous system for data. When a seat is booked or held on an edge node, that event is published to a Kafka topic. Other edge nodes and the central cloud can subscribe to these topics for real-time updates. This asynchronous messaging helps decouple services and manage data flow across the distributed system. The central cloud remains vital, acting as the ultimate source of truth, handling less time-sensitive tasks like complex analytics, long-term storage, and coordinating updates needing global consistency. Edge nodes handle immediate interactions, syncing via Kafka, while the cloud maintains the bigger picture. The paper describes a layered structure. A data collection layer gathers requests, an edge processing layer runs microservices on edge nodes orchestrated by Kubernetes, and a cloud integration layer handles persistence, large-scale analytics, and synchronization. This optimizes data flow, processing at the most appropriate location. Edge for speed, cloud for depth. So, what are the results? It's important to note this paper presents a conceptual framework, and its performance evaluation is based on simulations. These numbers aren't yet proven in a live airline system. However, the simulations are promising. The authors report a potential 60% reduction in average latency compared to traditional systems. That's a massive improvement in responsiveness. They also simulated a 20% increase in throughput, meaning the system could handle more concurrent users, and a 25% improvement in simulated user satisfaction metrics, likely tied to the smoother booking experience. This brings us to the so what for us as engineers. Firstly, it showcases combining edge computing and microservices to solve real-world latency and scalability problems. The patterns, edge computation, Kubernetes orchestration, Kafka for event streaming, are increasingly relevant across industries needing responsive, scalable systems. Secondly, it highlights inherent challenges. The paper is upfront about the difficulty of maintaining data consistency across potentially thousands of edge nodes. Imagine a flash sale. Ensuring every node has an accurate seat count in near real time without double bookings is a hard distributed systems problem. The paper suggests potential solutions like CRDTs and event sourcing. CRDTs, or conflict-free replicated data types, are data structures designed to allow concurrent updates on different nodes which can be merged automatically later to achieve consistency, though they have trade-offs, especially for data needing strong guarantees like exact inventory counts. Event sourcing involves storing all changes as a sequence of immutable events, providing history and fitting well with Kafka's streaming model for propagating updates. Managing this consistency effectively remains a major hurdle for real-world implementation. Another practical consideration is cost. Deploying and managing thousands of edge nodes isn't free. While the paper suggests potential cost optimization, there's an upfront investment and ongoing operational cost. Calculating the total cost of ownership is crucial. The paper proposes mitigation strategies like partnering with telecom providers, using managed cloud edge services, or a gradual rollout. Resource allocation is also key. Using Kubernetes autoscaling and predictive analytics to dynamically provision edge resources is essential. We also need to consider query types. Edge nodes excel at fast, localized lookups. But complex queries, like finding the cheapest multi-stop international itinerary over weeks, still require accessing vast global data. The framework keeps these large-scale analytics in the central cloud. The challenge lies in designing effective APIs and data sync between edge and cloud. The authors emphasize the broad applicability. The core principles could benefit supply chain management, remote healthcare monitoring, or smart city traffic control, any domain needing real-time, low-latency processing. Finally, the framework is presented as future-ready. Its modularity makes integrating AI for dynamic pricing, IoT for real-time tracking, or even blockchain for secure ticketing easier. So in conclusion, this paper presents a compelling conceptual blueprint for modernizing critical, real-time systems like airline reservations. By moving computation closer to the user with edge computing and embracing microservices orchestrated by Kubernetes and connected via Kafka, it offers a path towards significantly faster, more reliable user experiences. While simulated results are impressive, real-world implementation faces challenges, particularly around distributed data consistency and edge economics. However, for engineers building distributed applications, the concepts and trade-offs explored here offer valuable insights into architecting for real-time responsiveness. It's a vision where hitting book now feels instantaneous, even during the busiest travel rush. That's all for this episode of Podcast V0.1, and remember to never stop learning.